You ever drive past a massive industrial facility like an oil refinery and just marvel at the sheer scale of it all? Well, the amount of energy being controlled inside those pipes and towers is absolutely staggering. It's all held in a delicate balance by a complex web of engineering. Today, we're going to peek inside the rulebook that makes it all possible. So let's just ask the big question right up front, because this is the one that engineers have to live with every single day. With all that energy, all that pressure and heat, what happens if you lose control? The answer, of course, can be catastrophic. And that's why their entire job is built around making sure that never, ever happens. And they don't do it by guessing. They do it by following an incredibly detailed playbook called API Standard 521. This isn't just a boring technical manual. It's more like the collected wisdom of an entire industry. It's packed with decades of experience, lessons learned the hard way, and some brilliant engineering, all designed to keep that energy in the pipes. This is the blueprint for how to do it safely.
Okay, so how do you even wrap your head around designing for safety in a place that complex? Well, it all starts with one simple but powerful idea for how you think about what could possibly go wrong.
And that idea is called single jeopardy. The principle is pretty straightforward. You design your safety systems to handle one single, credible thing going wrong at a time. Not two things at once, not a crazy cascade of failures, but one. It's a really practical way of focusing on the risks that are actually likely to happen.
And this slide really lays it out perfectly. On the left, these are the single jeopardy events. A fire breaks out, the power goes out, a part fails. You absolutely have to design for each of these. But on the right, that's double jeopardy. A fire and a totally unrelated part failing at the exact same moment. The standard basically says the odds of that are so astronomically low, it's not a practical basis for design. And here it is, straight from the source. This quote makes it crystal clear. It gives engineers a logical framework. You can't design for a meteor strike and a power outage at the same time, but you absolutely must be ready for either one of them to happen on its own. So, with that single jeopardy rule in mind, what are these credible failures that engineers spend their time planning for? Well, this is where they have to imagine some truly terrifying but very possible situations. All right, let's start with a classic and one of the most dangerous scenarios, an external fire. Imagine a big pressure vessel full of liquid, and suddenly it's caught in a raging fire. What happens next inside that tank? Well, it becomes a race against the laws of physics. The heat from the fire makes the liquid inside boil, and boil fast. As it turns to vapor, the pressure just skyrockets. At the very same time, that intense heat is cooking the steel walls of the vessel, making them weaker and weaker. If you don't relieve that pressure, you know what happens next. And engineers don't just guess how much relief they'll need. They calculate it with incredible precision. This table is a little peek into how they figure out the exact surface area of a vessel they need to worry about in a fire. And see that 7.6 meters or 25 feet number? That's not random. It's based on years of data about how high flames from a ground fire are likely to reach. Every single detail is quantified. But not all dangers are as obvious as a big fire. What about a risk that's so fast, so violent, that your normal safety systems are completely useless? This is something called a superheat limit explosion. It's what happens when a relatively cold liquid, like water, suddenly comes into contact with a much, much hotter fluid. The water doesn't just boil, it flashes into steam almost instantly. We're talking microseconds. The expansion is so violent it creates a purely physical explosion, a massive shockwave. And here's the really scary part. You can't design a safety valve for this. A relief valve takes time to open, milliseconds, maybe a second. By then, the explosion has already happened. So the rulebook is very clear. For risks like this, the only defense is prevention. You design the system so that those two liquids can never, ever meet. Period. Okay, so we've looked at some of the problems. Now let's talk about the solutions. When overpressure happens in a scenario that a relief device can handle, where does all that dangerous energy actually go? It follows this very carefully engineered path. First, the pressure relief device automatically pops open. Then, all that gas rushes into a big network of pipes called a flare header. Now, when that valve opens, it's not a gentle hiss, it's an instantaneous, violent release. That creates a massive backward thrust, what engineers call a reaction force. It's a combination of the gas momentum and the pressure differential. For the valves that pop open instantly, structural engineers often use a safety factor, multiplying that calculated force by 2 just to account for the shock loading. The pipe supports have to be incredibly strong to hold everything in place. From there, the gas goes to a knockout drum, then up the flare stock, where it's finally burned off safely at the tip.
So this flare header, think of it as the emergency expressway for the whole plant. It's designed to collect a huge volume of gas from potentially multiple places at once and get it all to one safe place for disposal.
The knockout drum is a super important pit stop along the way. Its whole job is to get any liquid droplets out of the gas stream. Why? Because you never want to send a slug of liquid up to the flare. That's extremely dangerous. The drum is basically a big, wide spot in the road where the gas slows down and gravity can pull the heavier liquids out. And none of this is guesswork. Sizing these massive pipes and vessels requires a deep understanding of physics. Charts like this one show the complex behavior of fluids under different pressures and temperatures. Engineers use this data to predict exactly how things will act during an emergency, making sure every part of the system is up to the task. And the safety planning extends all the way to the people working on the ground. The standard specifies this number, 6.31 kilowatts per square meter. That's the absolute maximum heat radiation a person can be exposed to. And that number directly determines how tall the flare has to be and how far away it must be from any workspaces. It's a perfect example of a calculation directly protecting human lives.
So let's step back for a second and pull all of this together. After seeing all these details and calculations, what's the big picture here?
The most important thing to realize is that safety at this kind of scale is never an accident. It's not about crossing your fingers and hoping for the best. No, it is a meticulously planned, designed, and engineered outcome. Every single valve, pipe, and support is part of a system that's built on foresight, the ability to look into the future, anticipate failure, and design a solution before it ever happens. And all that knowledge is captured right here, in documents like API 521.
And this final quote really sums up the responsibility involved. Look at that word shall. That's not a suggestion, it's not a guideline, it's a command. It is a direct order to the engineer. You will do this calculation. You will ensure this equipment is protected. There's no room for error. You know, most of this incredible safety engineering is completely invisible to us in our everyday lives, but it is working all around us. It makes you wonder, doesn't it? What other hidden rulebooks and unseen designs are out there, quietly keeping our modern world from falling apart?